Welcome to the next video, 6.3 part 1. So you'll notice that we dance around a little bit. We've started with 6.1 and then 6.3 is about proving identities, and we're going to do a mastery check 6.3 part 1, and then we'll do 6.2, and then we'll do 6.3 part 2. So there will actually be two mastery checks on proving identities. So the first one is sort of like the intro to it, and the second one is where we add things like double identities and things like that. So first of all, what is proving an identity? It is manipulating both sides of an equation independently until they are identical. And so we did a little bit of it earlier, but now we'll do a few more. Here are some hints to take a look at, so if you get stuck you can take a look at this. Most times my first step is to rewrite all the functions in terms of sine and cos. Other things to try out are to factor, to multiply by 1. So when we multiply a fraction by sine theta over sine theta, really that's the same thing as multiplying by 1, which doesn't change anything. To simplify, like to cancel like terms, to expand, like if we're multiplying two binomials, and sometimes, and we'll see an example of this, I think, we multiply by a conjugate. So if you've got something like 1 over 1 plus cos alpha, you might want to multiply by 1 minus cos alpha over 1 minus cos alpha. So here's an example of multiplying by 1, because really this is multiplying by 1. And why would you do that? Well, it's these two terms in the denominator, and you'll notice that's got the difference of squares pattern to it. So the result of when you've multiplied those two out would be equal to, in the denominator, would be 1 minus cos squared alpha, because it's like a plus b times a minus b. The middle two terms cancel out and we get a squared minus b squared. The numerator in this case would be 1 minus cos alpha. So that would be a case that we use every once in a while. Especially when you're stuck, consider that, or if you ever see sort of a pattern. Some things to remember. Identities are different from equations, so we only work with one side at a time. That's what I mean by keep sides separate. And there's usually like a t that's like that. So just work on this side by itself, and then if you want to, you can work on this side, but you're not going to like multiply both sides by 2, for example, that you do on an equation. You only work on one side at a time. When you're done, the traditional way to finish is to say left-hand side is equal to right-hand side. That's the short term. And work vertically, so don't write this equals this. Just write another line. If you need more space, ask for an extra sheet of paper. The other thing that we're going to be using a lot are these identities, and sine squared plus cos squared theta equals 1 we talked about earlier. Now that is on your formula sheet, so I'm just going to whip over to your formula sheet. You should have one of these, and you can use it for every mastery check, you can use it for every test, and you'll get one probably exactly like this for the exam. And so this is in this section on the top left hand side, and I would like to refer to them right now. So if you see at some point a sine squared plus cos squared, you can substitute that for 1. So let's say if you had on one side you had sine squared theta plus cos squared theta, and this was on the left hand side, on the next line you could just write 1 because those two things are equal. I'd like to also point out that we can rearrange this and we get some interesting things. So out of this there's two important ways of rearranging it. We could solve for sine squared theta. So in other words, 1 minus cos squared theta is equal to sine squared theta. So anytime you see 1 minus cos squared theta, you can switch it for sine squared theta. And the other version of that would be 1 minus sine squared theta equals cos squared theta. Those ones happen a lot, okay? I'm just going to mark those ones now as the most important ones, and these will happen sometimes too, but if you do the first step of switching everything to sine and cos, you probably won't be using those ones as much. Alright, let's try it out. So turn to the next page. My first example says prove the following identities for all permissible values. So I'm going to do that initial step of changing everything to in terms of sine and cos. I'm also going to say that, hey, I'm going to work with the left-hand side. So I'm just going to say left-hand side. And I'll say, okay, well, sine of x, I'll rewrite that, times secant is the reciprocal of cos. So here I'm going to write 1 over the cos of x multiplied by cotan. So remember that tan is sine over cos, and cotan is cos x over sine of x. So I'm just working with the left-hand side, so I'm not writing equals 1 at this point. Now I'm going to say, oh, okay, well, yeah, since this is all multiplying, I can do some canceling each other out. Cos x divided by cos x, or cos x over cos x is equal to 1, so I can cancel those out. Sine x is going to cancel each other out as well. So my final answer here is just going to be a 1. And I'll notice that that is the same thing as the right-hand side. So I can say equals the right-hand side. So it's kind of like I said, left-hand side is equal to this, which is equal to the right-hand side. Or I could also go, you know, I'm not too picky, as long as at some point you make it very, very clear that you've shown that the left-hand side is equal to the right-hand side. Okay, how about the second one here? We have 1 plus sine theta over 1 plus cosecant theta. So again, I'm going to work with the left-hand side. And I'll say 1 plus sine theta, or sine alpha, pardon me, over 1 plus, now cosecant is the reciprocal of sine, so I'm going to say, 1 over sine theta, sine alpha. Now, looking at the denominator, I got 1 plus 1 over sine alpha, so I would like to put this whole section over there, there's 2 terms in the denominator, I'd like to put them as 1 term. So that 1 I'm going to change to sine alpha over sine alpha. Here I'll just write the numerator again. Plus 1 over sine alpha. So I'll just highlight the similar here. If I get rid of this, there, this 1 turned into this. This is what I changed, okay? And again, don't try to do a whole bunch of steps all at once. It's okay to make only one change at a time and to show lots of work, because we already know what the answer is. We already know that the left-hand side is going to equal to the right-hand side. The point of the work is to show the steps, so don't try to jump any of them. All right, so my next part will be 1 plus sine alpha is all over 1 plus, oh, no, sorry. I'm going to undo that. I need to put these 2 terms in the denominator together. So when I put those 2 terms together, I will get sine alpha plus 1 all over sine alpha. In fact, now since I need more space, I'm going to go back over here. All right, so I've got, this is my large fraction bar. So my numerator is 1 plus sine alpha, and my denominator is sine alpha plus 1 over sine alpha. So often we're going to be doing this. Dividing is the same thing as multiplying by the reciprocal. So I'm going to say 1 plus sine alpha times, now I'll do the reciprocal, sine alpha over sine alpha plus 1. Now I see that, hey, when I've got these fractions, I've got this term here and this term. With adding, it doesn't matter which order you add, right? 2 plus 4 is equal to 4 plus 2. These 2 terms are exactly the same, and since they're all multiplying and dividing, this is like another version of 1. When I cancel that out, that would be the same thing as 1 times sine alpha. So my final answer here on the left-hand side is going to be sine alpha, and that's what the right-hand side. So I'll just say equals the right-hand side, and then we're done. Let's check out C here. Again, the left-hand side is the complicated one, so let's work with the left-hand side. And I'm going to say secant x all over. Now I'll change tan of x is equal to the sine of x over cos of x plus, now cotan is the reciprocal, would be cos of x over sine of x. Now it's kind of like our similar, the part B, the previous question, in that I've got this complex fraction with these 2 fractions in the denominator. What I want to do, maybe I'll just rewrite this and put some space here. I'm going to go like this, plus cos of x over sine of x. To combine these two fractions, just like if I had, say, 1 plus 3 over 1 plus 4, I would have to make them into a common denominator. In this case, it would be a 12, right? And if I would say, oh, I need to multiply this times 4, so I'd multiply this times 4. So this would be 4 over 12 plus 3 over 12. So I'm going to be doing the same thing with that denominator. My lowest common denominator here is going to be sine x cos x. And here I had to multiply this times 3, or this times 4, and times 4. Here I'm going to multiply this times sine of x over sine of x. Here I'm going to multiply this by cos of x over the cos of x. So again, what I've done is multiply things by 1, sine of x over sine of x. This just has a value of 1. But the result is now I've got the lowest common denominator. So I've got secant x all over. This will be sine squared x over cos x times sine of x plus cos squared x all over sine of x times cos of x. I'll erase my work over here. Okay, so now these are the same. It doesn't matter which way you, which order you multiply. So I can combine those two. So in my next line, I'm going to write secant x all over sine squared x plus cos squared x all over, I'll put sine first, sine x cos x. Okay. Oh, and secant x, I should probably switch to 1 over cos of x. There we go. If I'm going to follow my switch things. Now you might say, oh, what has that done? It looks even more complicated than it used to. Well, the thing that pops out at me is this sine squared x plus cos squared x, which, hey, that's equal to 1. Good news. So in my next line, and I'll just go over here, I'm going to say 1 over the cos of x all over 1 over sine of x times cos of x. And now again, I'm going to use the old dividing is the same thing as multiplying by the reciprocal. Multiplied by the reciprocal of that would be sine of x times the cos of x all over 1, and then I get to cancel stuff out. I get to cancel these two out, and then I will have sine of x as my answer, and that is equal to the right-hand side, and everybody is happy. There we go. All right, let's look. Now we're on the second-hand page. So here's an example where you might be working both the left-hand side and the right-hand side. Up until now, we had examples where the right-hand side was, just a very simple term. So all we needed to do was work the left-hand side. So now that we've upgraded to this part, there's this nice t that's been given to us. So we're just going to work the left-hand side on the left-hand side of the t and work the right-hand side on the right-hand side. So I'll start off by saying 1 minus cos squared theta is the left-hand side, and I'll just put this cos squared theta times tan squared theta. And just a reminder, write your thetas in every time, or your x's or whatever they are. Because if you drop it, it's kind of like breaking the grammar of math, and you lose marks and all that stuff. Okay, hey, 1 minus cos squared theta. That reminds me of, remember, well, I looked at this, where would that be? That's this one, isn't it? That's this 1 minus cos squared theta is equal to sine squared theta. So I'm not sure if I need to do it or not, but probably I will. So I could just say, hey, that's the same as sine squared theta. And that's kind of as much as I can do on the left-hand side. Let's look on the right-hand side. Cos squared theta times sine squared theta over cos squared theta. Okay, so if tan is sine over cos, tan squared is going to be sine squared over cos squared. And then I can cancel those two out. Look, we're there already. So then I get sine squared theta, and then I can write left-hand side equals the right-hand side. We did it. Okay, let's try E here. All right, cos squared x over cotan of x, sine x, cos x. Now, let's work on the left-hand side because it's a bit more complicated. And let's simplify that cotan as cos x over sine x. And now let's do the changing the dividing into multiplying by the reciprocal. So I'll have cos squared x multiplied by the reciprocal of that denominator. And then I see, hey, this is cos squared and this is cos, so I can cancel this out and then just one of those two coses. And then I can say, hey, it's the same, but you know what, why don't I make it really official by rewriting this as putting sine x first and then cos x second, and then I can write left hand side equals right hand side. So you see how sometimes these are kind of like puzzles that you have to, you know, or maybe knots where you have to pull at a string and see, hopefully it'll all come undone. Let's look at part F. Oh, this is a fun, crazy one. I've got the, you know, I've done these a few times, so I recognize the pattern right away. So when I see this, this is the part that might scare people, the cos to the power of 4. Okay, so what this really means the same thing as, like, it'd be similar to a to the 4th power minus b to the 4th power, right? When I look at that, I see a difference of squares. Like, so just as a reminder that difference of squares, the typical way we write it is that like a squared minus b squared is equal to a plus b times a, here, let's get this over here, a minus b, oops, times a minus b. But in this case, it's going to be a to the 4th. So let's see, a to the 4th minus b to the 4th. Well, it would be, what's the relationship here? From a squared to a is the square root. The square root of a to the 4th would be a squared. A squared plus b squared times a squared minus b squared. Maybe you did this in grade 11, I'm not sure. And then what's cool about this is that this can be also factored using the difference of squares. So before I finish it there, let's just use it instead of a's and b's. Let's do it with cos and sine. So I'll go over here. I'll write cos to the 4th theta minus sine to the 4th theta. Now when I factor that, I will get cos squared theta plus sine squared theta times cos squared theta minus sine squared theta. So, and then I can factor out this one using the difference of squares again. So I can say, oh, and maybe I should do this first. This one here is equal to 1, isn't it? So if I write this again, this would be equal to 1 times cos squared theta minus sine squared theta. You know what, I'm just going to stop there and I'll see how the other side looks. Here I have 1 minus 2 times the sine squared theta. Is there any way that I could use those trig identities that we talked about before? Let me just see if I can grab a copy of them. I'll be right back. Alright, so I put a little copy down on the bottom from our earlier in our exercise. So I'm looking at this cos squared theta minus sine squared theta, and I'm looking at this 1 minus 2 sine squared theta, and I'm thinking, well, here is an interesting thing I can do. This cos squared theta is equal to 1 minus sine squared theta. So I'm not sure if do you see where I'm going with this? I'll switch to green. I'm going to say that that this cos squared theta I can substitute with 1 minus sine squared theta. So let's do that. I'll say 1 minus sine squared theta, and then this other minus sine squared theta still stays there. Okay, so now I've got 1 minus 2 sine squared theta, and now it looks the same on the left hand side as on the right hand side. So I can say, switch to blue here, I'm going to say left hand side equals the right hand side. Okay, so again, there's more than one way to do this. You could have solved it and worked on the right-hand side for a while as well. This is the steps that I used. These trig identities, a lot of it is about practice. So I highly recommend that you go and take a look at the homework and try those exercises 1 to 10. Thanks, and I will see you in class.